So you're probably going to hear from two of the best scientists in the country this afternoon. So, so don't moderate your expectations. So, so the first of these is Dr. Sarah Badman from Lancaster University, who was awarded her Aurorae Fellowship for 2012 to 2015. And she's going to talk about the aurorae of Jupiter and Saturn. Sarah.
Yeah, thank you very much for inviting me to give this talk. So yes, I started my fellowship actually in early 2013 at the University of Leicester, and then I've been at Lancaster for most of it. So the topic of my research is, as you can see, the very beautiful aurora of Jupiter and Saturn. The picture on the left is an artist's impression showing some recent results about these auroral explosions at Jupiter, using a couple of the facilities that I use in my research. So it's a couple of Earth-based telescopes, the Hisaki one, which is owned by the Japanese Space Agency, and the Hubble Space Telescope, which you're probably quite familiar with. On the right is an image of Saturn, different infrared wavelengths taken by the Cassini mission. So Cassini's been at Saturn since 2004, and it's built up a real wealth of data. And one of the things that we can do with Cassini at Saturn is get much better observations of the aurora because they're quite faint. So here you're seeing reflected sunlight in blue, thermal emission in red, and the aurora in green. So I want to just show you a bit about the motivation for the work that I've been doing, and then a couple of recent key results. So I don't have time to go through 3 years' work. You're probably grateful for that. Okay. So the objective of my research program is basically trying to find out how the sun affects the space environment of the planets. And that's nicely illustrated on this schematic here. So you've got the sun over on the left. The sun's atmosphere is constantly streaming away into space. It carries the sun's magnetic field with it. And when this is out in space, we call this the solar wind, and it flows past all the objects and planets in our solar system. So the planets I'm going to be talking about and the Earth are magnetized, and you can see the magnetic field lines shown here, these blue lines. And these form a region in space called the magnetosphere. So this is just the name for the region that's dominated by the planet's magnetic field. And this also shows how these two regions can interact. You've got the solar wind coming in and kind of squashing the planetary magnetosphere, which is an obstacle to the solar wind flow. But some of the particles that are carried out in the solar wind can become trapped in the planet's magnetosphere, and they precipitate down into the atmosphere and generate aurora. So that's what's shown in this movie here. Again, you're starting at the sun, a good place, important place to start. The sun's atmosphere streams away into space. So this is electrons, protons, helium, carries the sun's magnetic field with it. And when it reaches an obstacle like a planet's magnetic field, the two magnetic fields can interact with each other and allow the transfer of energy and momentum. So some of those particles can get trapped in the planet's magnetosphere. So they can travel down the magnetic field lines into the atmosphere on the day side, but also they get carried into the night side, and you get this magnetic field reconfiguration. It accelerates particles back towards the planet, and that's what produces the aurora. So this is basically what we know drives the system at the Earth. It's very much controlled by the solar wind. And so you imagine if you have a change in the solar wind, like a higher pressure region, that can generate different aurora. And that's one of the things we try to use to predict whether people are going to see aurora. Unfortunately, I was on a plane and missed the aurora earlier this week, which is typical. Anyway, I went to a meeting to talk about aurora and missed actually seeing the aurora myself. So these are some images of the planetary aurora. We've got the Earth, the familiar one on the left, Jupiter in the middle, and Saturn on the right. And so these are composite images, false colour ones, obviously. And you can see that basically they have some similarities. They're kind of an oval shape around the pole. And this is because they're formed by particles travelling down magnetic field lines. So you get that ring around the magnetic pole. But particularly in this image of Jupiter, you can see there's a lot more going on than just an oval. We see this dot down here, which is actually a footprint of one of the moons, and I'll show that again in a second, but also lots of dynamics at high latitudes. So it's not quite the same system. So the approach of my research is to use images like the ones I showed you of the aurora, because they provide snapshots of the dynamics of the whole magnetosphere. So it's like a TV screen for all the plasma in the magnetosphere, and where it's precipitating down and exciting the aurora. So if we see changes in the aurora in time or in space, that's telling us that those regions out in the magnetic field are changing as well. So this schematic here nicely shows the connection between the different regions out in the magnetosphere and the planet's atmosphere. So here you've got like magnetic field lines shown in this turquoise colour, and also these moons and their magnetic field lines travelling down into the planet's atmosphere. So one word I'll probably keep saying is mapping, and what I mean by that is if you have something out in the magnetosphere, you can map it down along a magnetic field line into the planet's atmosphere. So, moving on to Jupiter. So Jupiter is, as I'm sure you know, the biggest planet in the solar system. It's the fastest rotator with a less than 10-hour period. It's got the strongest magnetic field, and it's also got the strongest internal plasma sources. So previously we were talking about the solar wind as being the source of plasma that drives the Earth's aurora. But here at Jupiter, we've got to consider these moons deep inside the magnetosphere. So how do we actually get the aurora at Jupiter? So it all starts with this volcanic moon, Io, which is the most volcanically active body in the solar system. It gives off about a tonne every second of sulfur and oxygen into its local environment. And obviously some of that can be ionised and picked up by the magnetic field. So as this iogenic material moves out, it starts to slow down to conserve angular momentum. And so the magnetic field lines that it's on get bent out of their meridian planes. So it starts to sort of be lagging. It's not going as fast as the planet is rotating. It's lagging behind that. And we get an electric current system set up which acts to transfer angular momentum from the rapidly rotating planet out into the magnetosphere. And this is trying to speed up all of the magnetic field to co-rotation with the planet. So this field line current system is shown here. So you've got an upward current, it goes out through the equatorial plane and returns at higher latitudes and closes in the ionosphere. So if you've got an upward current, that means downward electrons, and therefore you've got energy precipitating into your ionosphere, your atmosphere, which can give the aurora. So there are two things here which we can see will give variability in the auroral currents and hence the aurora that we can see. One is compression by the solar wind. So this is all surrounded by the solar wind flowing past it 400 kilometres a second. And if there's a shock in that and it squashes the magnetosphere, then these field lines will all be moved in. And that means as they move in, they speed up, and you need less current to keep them co-rotating with the planet. So that's one way that the currents can change. And the other way is if you have a change in the mass loading from Io. So for example, if its volcanic activity changes, there can be more or less stuff available to be picked up by the magnetic field. So we have an external and an internal control at Jupiter. So this is one of the nice HST images in the UV. So you're looking at Jupiter's northern aurora. And here the features are labelled. So you've got the main auroral oval, which is very clear on this side, but actually isn't really oval like on the other side. It's deformed into kind of a kidney bean shape and made up of sometimes multiple arcs. You can see the footprints of the moons. So remember from the previous schematic you had like magnetic flux tubes going down from the moon into the planet's atmosphere, and that's the signature of these. And then here we've got the polar aurora, imaginatively named, which is at higher latitudes, and this is very dynamic. So one of the things I did as part of my fellowship was I had time observing on Hubble Space Telescope to look at both Jupiter and Saturn, and this is a movie of the Jupiter observations that we got in January 2014. So they were spaced over 2 weeks, and you're looking at 100-second integrations, and basically you can just see the dynamics, right? It's very variable. The most constant thing is the sort of the main oval shape, but actually everything going on at high latitude and at low latitude is incredibly variable. So we wanted to understand what's driving this variability. Is it Io? Is it the solar wind? So this is now a snapshot from each of the day's observations that we had. So you're going across in time like this. They're separated by roughly 1 Earth day. And the view is now you're looking down on Jupiter's north pole. So you can see the main aurora and the moon footprints sometimes outside that. And what I want you to notice from these is if you look at, for example, the first 2 images here, you can see that the main oval on Jupiter is very bright and very narrow, particularly on this dawn side. And if we go just 2 weeks later, you can see that it looks very different indeed.
Sorry, is this the north magnetic or the north Jovian pole? Rotation pole? It's
both, but so the aurora are centred around the northern magnetic pole, but that is in the northern Jovigraphic pole.
Yeah, but they're offset by 10 degrees.
Yeah. So the Jovigraphic, so like the spin pole, is this shown this dot here. So that's what the grid is. But the aurora is offset from that, so it's around the magnetic pole. Okay. So we can quantify this change in the auroral emission that we saw. The Hubble STIS instrument has great spatial resolution and temporal resolution. So not only can we work out the total power from the whole auroral region for each image, we can also divide it up into different sections. Okay, so that's what's shown here. You've got a time series across the 16 days of observations that we had, and then this is power on the y-axis. So in the top panel, these crosses show you the total auroral power that was emitted in each of these images, and you can see it is decreasing over the 2 weeks that we observed. And this most closely follows the variability in the main oval region, which is this just 2 degree wide strip centred on that peak emission. So here you can see this kind of trend, and it's actually decreasing by about 70% over 2 weeks. So it's a really significant decrease in the intensity and the power that we're seeing. So we want to look what could be driving this auroral activity. There were ground-based observations of Io's sodium nebula. So this is neutral sodium that's released through the volcanic activity. So this is from the end of 2013 until January 2014, and this is brightness from the sodium nebula. And it's actually pretty constant. In previous years, when there's been a significant sort of change in the activity, it's increased by a factor of sort of 4. So we're not seeing that variation here. It looks pretty steady. So it doesn't look like there's any change in the mass loading from Io that could be driving what we saw. We could also look at the solar wind observations, and what we do is take measurements from a spacecraft near Earth that measures the pressure in the magnetic field in the solar wind, propagate them out to 5 AU, which is where Jupiter is, and this is the propagated solar wind dynamic pressure here. And remember I said that if we compressed the magnetosphere, it made everything spin up and we needed lower current. Well, actually here the pressure is decreasing, so we expect our magnetosphere to be relaxing and expanding. So, that's not matching up with the theory that we had before. So actually there's this, it's unexpected variability. It disagrees with the previous theories that we had, but it looks like it's actually this decrease in dynamic pressure is quite well correlated with the decrease in power. So we need to go back and work out, make this simple theory more complicated to work out actually what's going on. Okay, so moving on to Saturn. So Saturn is also a fast-rotating gas giant, and people sometimes call it a hybrid between the Jupiter and the Earth. And it has some similarities with both. So again, you've got the solar wind interaction. That's coming in on the left in this schematic. There's the planet. But it turns out one of the major discoveries of the Cassini era was that there was a significant source of water in Saturn's magnetosphere, and it was coming from this tiny little moon Enceladus. And this has ice plumes coming from its south pole, which was a big surprise to lots of people. And this is therefore a significant contributor of mass into Saturn's magnetosphere. So this is telling us we don't need to just worry about the solar wind. Again, we've got to worry about what's happening inside the magnetosphere. This is a typical view of Saturn's aurora. So again, you're looking down on the North Pole. And in the case of Saturn, the spin and magnetic axes are very closely aligned. So the oval is centered pretty much on the spin axis, with a caveat that I'll come to in a second. You can see the main oval is generally brighter at the dawn side. There are these transient features around local noon, so that's the direction towards the sun, which is at the bottom here. And we see this diffuse emission as well. So again, it's not purely a nice symmetric auroral oval. This is a press release movie, which is always nice to show, from some combined observations that we had in spring 2013. So the first few images were from Hubble, which is near Earth, so that's where you could see the rings and the planet. And then these are images taken at different wavelengths by Cassini, so actually in orbit around Saturn. That's infrared. This is the UV seen by the Hubble Space Telescope. And the next one is UV seen from the Cassini orbiter, so you can tell it's actually flying over the pole at this time. So I said that Saturn's magnetic and spin axes were very closely aligned, but actually it turns out that there are many features in Saturn's magnetosphere which behave as if they're not aligned. Okay, there's this kind of planetary period oscillation in many different features. And one of them that we're interested in here is the rocking of the auroral oval. So it's been shown from lots of studies now that if you imagine the oval as a circle around the pole, it actually kind of tilts backwards and forwards with a magnitude of about 1 to 2 degrees every Saturn rotation. And so it looks kind of like you would have an offset dipole. Imagine that spinning round, then the auroral oval position would shift. But remember, at Saturn, they're actually aligned. So we don't know what's causing this offset and this oscillation. So I'm just going to show you a couple of slides about more in detail from that campaign in the movie. So this is April 2013. These are auroral images taken by different instruments. Again, you're looking down on the pole. The direction to the sun is at the bottom of each of them. If you're interested, the one on the top is infrared wavelength, and the bottom two are ultraviolet. So this is going out to about 25 degrees from the planet's pole. You can see the bright emission around here on both sides. A couple of other things to point out. This white line is the trajectory of Cassini mapped down into the atmosphere. So remember I said you take its position and trace it along a magnetic field line. That's where it is in the atmosphere, its footprint in the atmosphere. And the other thing to look at is this yellow arrow here that's on each of the images. And this is the direction in which we expect the auroral oval to be tilted. So it's got that 1 to 2 degree oscillation. It's rocking backwards and forwards every 10 hours. And that at any given time, we can predict where we expect it to be tilted. So this is comparing the position for the two images. And you can see that, so the first one is the one shown in blue. This blue solid line shows the peak auroral intensity from this image. And the blue arrow is the direction it should be offset towards. And red is for the later one. And basically you can see that the auroral oval is tilting away from dusk, which is over here. So the blue line is more over to this side than the red line, basically. Thank you. And so this is consistent with what was predicted. You can see that's lining up with where these arrows say the main oval should be located. But then on the next day we had a sequence more images, and you can see there's a lot more dynamics going on. It's a lot brighter. There's this bulge here, and then a poleward motion of the aurora here. And this is the same format. And so again, we can look at this rocking and see if that's still happening in this more dynamic interval. So now we've got more images to compare, covering about half a planetary rotation. So at the start, shown by the blue, it should be offset towards the dawn side, this far side here, and at the end it should be offset over here. And it should be the auroral oval should be at its most sunward position at the time of this green image, the third image. But actually, if you look at the position of the red line, like here, the aurora continued to move poleward after that. So it keeps moving towards the sun. So this is opposite to what was predicted by this sort of quiet time rocking of the auroral oval. So because Cassini was travelling through these field lines, it's not only taking images, but it can measure the fields and particles, and so we can look at the auroral currents, so the flow of the particles. And that's what I'm showing here. It's a bit blurry, sorry, but it's about 12 hours of observations in each panel. The bottom is the a component of the magnetic field, and you're a physicist, you'll know if you have a curvature in the magnetic field, that's a signature that you've got a current. And so from this like sharp change in the magnetic field that Cassini measured, we can infer the presence of an electric current flowing. And these purple regions here are the regions that are the upward current, which remember is the downward electrons, which gives us the aurora. So we're actually measuring the electrical current associated with the emission that we're seeing. And basically, if on this second day, from the second sequence of images I showed you, this current was about twice as strong as it was on the previous day. And how do we interpret that? If you look at the top panel, this is radio wave observation. So this is like the auroral radio emission as a remote proxy for what's going on. And you can see it's much brighter and extending to lower frequencies here on the second day than it was on the first day. And this is a signature of a compression by the solar wind. So in this case, we're seeing that the solar wind compression not only caused the intensification of the aurora, but it also, you can measure that effect in the field line current, and it's disrupted that rocking of the auroral oval. So that's just a couple of very brief results from what I've done. So to summarise, we saw this significant decrease in Jupiter's auroral power, and it shifted slightly equatorward over 2 weeks. And there was no apparent trigger in the two features that we expected to trigger it, which was Io volcanic activity or a solar wind shock. And then looking at Saturn, we've seen that the oscillation of it, which is a really characteristic thing in Saturn's magnetosphere, is disrupted when you have this solar wind compression, and you get this intensification of the auroral currents. So what's next? This is actually a very exciting year, this year and next year, for planetary auroral studies, because the Juno mission will arrive at Jupiter in just a few months. It's going to go into an inclined orbit, which is perfect for flying through these auroral field lines and taking great images looking down at the poles. And similarly, Cassini is going into the grand finale of its mission, and at the end it will be passing between the inner edge of the B ring and the planet, so really close and really low down through this auroral region. So I'd just like to thank the RAS very much for supporting my fellowship for 3 years, and also to the Cassini, Hisaki, HST and ISI teams for their collaboration. Thank you.
So we have a few minutes for questions, if anybody has any. Right to the back there.
So,
Can you just wait for the microphone so that we can...
so on the Earth you have aurora in the north and in the south. I presume you have similar features on the planets. And if yes, are they symmetric? Are they conjugate?
That's a good question. Yes, there are auroral ovals both at the north and the south. At Jupiter, they're definitely not symmetric. So remember, Jupiter had that kind of kidney bean-shaped auroral oval, whereas in the north, whereas in the south, it's much more circular. And this suggests there's some magnetic field anomaly that's distorting the auroral oval in the north. At Saturn, they're more symmetric, but actually one of the studies we're trying to do with some observations this year is have Hubble look at the north while Cassini's looking at the south, and actually do that study of how symmetric are they, and that tells us about what's causing the precipitation in both hemispheres.
Around there. And then Lindsay.
Is there aurora at Uranus and Neptune?
There are aurora at Uranus and Neptune, yeah. They've been seen by Voyager and also very faintly by Earth-based telescopes, but it's pretty difficult to see from the Earth. Yeah.
There's Lindsay at the back.
Do you have simultaneous imaging of the aurora in different wavelengths, and can you tell if there's any offset between the locations at different wavelengths, particularly X-rays versus optical, say?
Okay, yeah, so it's actually proven incredibly difficult to get simultaneous observations at different wavelengths, but we do have them thanks to Cassini, particularly at Saturn. And there are some different features which suggest either, for example, the infrared emission responds to the temperature of the atmosphere, and so therefore it can have a slightly different profile than the ultraviolet precipitation. I won't talk about X-rays. Will, who sat in front of you there, is the expert on the X-rays, which we have seen from Jupiter. And they do line up quite well with the ultraviolet. But, yeah, it's not exactly the same emission mechanism. Yeah.
Okay, any more questions? Otherwise, let's thank Sarah again.
Thank you very much.